Hey guys, this is Mr. Bond. I'm just going to run through continuity, which is the third standard in the honors calculus curriculum. Continuity is going to be included on your next assessment, along with standards 1 and 2, local and global limits. So one definition of continuity is that a function whose outputs vary continuously with its input and do not jump from one value to another without taking on the values in between is said to be continuous. I don't like this definition at all. I prefer a very simple, practical definition. If you can trace a function without lifting your pencil, then that function is continuous. So the big idea here is we are just tracing functions. So if I have some sort of a function here that I'm going to create, let's make it some sort of a piecewise function. I'll say that I have a closed circle right around here, and you can see my piecewise function. So if I start to pull out my highlighter and I try to trace this function from left to right, I never have to pick up the highlighter to finish tracing. So because I never had to pick up the highlighter, that is a continuous function. Conversely, I can create another piecewise function. Got a closed circle here, and we have our distinct pieces. And I can trace this function from left to right using my highlighter again. So I break out the highlighter, and then as soon as I get to that open circle, I have to jump down. So I had to lift my pencil right at that open circle to the closed circle. So the function on the left is continuous, the function on the right is not continuous. And it's all about whether or not you have to lift your pencil or your highlighter when you're tracing it. All right, so one of the most important questions you're going to be asked is to identify the intervals over which a function is continuous. So even though this is clearly not a continuous function because we see a couple of issues, we can talk about where it is continuous. So I'm just emphasizing my closed circles, and we're going to start from left to right. So starting at x equals 0, our function is continuous right up until we get to 1, where we have that open circle. So our function starts at 0, and then at 1 we have an issue. So because it's not continuous at 1, I'm going to use an open parenthesis for my 1 because of that open circle and because of that jump that we see right there. That jump is literally called a jump whenever you go from one y value to another over the course of your interval. So we have a jump, and that's going to create my open parenthesis. Now my function continues, and it continues starting at 1 again with an open parenthesis. And the next place that I have an issue is at 2, because at 2 we have this little hole, and we have the closed circle above it. So because we have a discontinuity at x equals 2, I'm again going to call that a hole. That is the technical name for it. And I'm again going to use an open parenthesis at x equals 2 while I'm naming the intervals of continuity for my function. So I put a 2 with an open parenthesis because the function is not continuous at 2. When's the next place that it starts up again? Right again at 2. And our function, if we travel along this function from 2, we get to 3 and we have to change directions, but that's not a big deal. It's still continuous. I still don't have to lift up my pencil. The next place that we stop is at 4. That's where the function stops, and we're going to use a closed bracket because we have a closed circle at the very end. So this is our interval of continuity, and it aligns with what's happening with our function. Our function is continuous from 0 to 1, from 1 to 2, and from 2 to 4. And I can specifically name the places where we have discontinuities. So we would say that at x equals 1, we have a jump, and at x equals 2, we have a hole. So I just want to formally define these different types of discontinuities. There's 3 in this class. The first one is pretty simple. It's a hole. You're traveling along your function, and we reach a hole at x equals c in this case. So I'm just going to define that. It's a hole regardless of whether or not there's a closed circle at some point above it. So I could put a closed circle up here, and it's still a hole at x equals c. We can't trace our function without lifting our pencil at x equals c. The next type of discontinuity is a jump, as we saw before. I can create a quick sketch and create some sort of a piecewise function here. And if we look at our piecewise function, it's clearly not continuous. I can identify where that we have a discontinuity right at that x value. We could call that c again if we wanted to. So let me just label that as x equals c. We have a jump at x equals c, the y value at c drastically changes. It is a function because one of them is a closed circle and one of them is an open circle. It could be two open circles as well. It would still be a jump. And if I trace my function, I have to lift my pencil at x equals c, so it is not continuous. The last type of discontinuity that we're going to look at is an infinite discontinuity. So for this one, I'm going to look at a specific function, y equals 1 over x. And we know the rough sketch of this from pre-calculus. There's two pieces. If I break out my highlighter and I try to trace this function, I have to lift my pencil at x equals 0. And we can also see that the limit from the left goes to negative infinity and the limit from the right goes to positive infinity. Because we're heading towards infinities in both directions, we have what's called an infinite discontinuity at x equals 0. The infinite discontinuity goes hand in hand with the vertical asymptote. So sometimes you'll be asked to find points of discontinuity, and it's important to know where your discontinuities are when you're given a function so that we can do some calculus with these functions. So if I look at 1 over x minus 2, I know that I have an issue at x equals 2. The question is, which type of an issue is it? If I create a quick sketch of this function, I recognize this is a rational function with two distinct pieces, and I recognize the fact that I have an infinite discontinuity occurring at x equals 2. Another rational function here, 1 over x squared plus 2. Again, we're going to take a look at the denominator, and we're going to set it equal to 0 to figure out where we have an issue. So if I set x squared plus 2 equal to 0, I'm asking myself which x values are going to be a problem. And when you solve this, we get plus or minus I root 2. Since that's an imaginary number, that means there are no real values where we have issues. Therefore, this is a continuous function. There are no points of discontinuity. You can trace this function without lifting your pencil. Another example that is sort of a review of your pre-calc skills. If you have a rational function like this, we want to factor it first, and we want to cancel out our common factors. Because x minus 4 cancels out, that means that at x equals 4, we have a hole on our graph. So I'm just going to identify that as one of my discontinuities. We have a hole at x equals 4. Now our simplified function is now 1 over x plus 4. So examining that denominator, we have a denominator of x plus 4. That means that we have an issue occurring on our graph at x equals negative 4, and that's going to be an infinite discontinuity because I know the shape of the 1 over x plus 4 graph. So we have an infinite discontinuity at x equals negative 4 and a hole at positive 4. So what about a log graph? Do we remember the shapes of log graphs? Logs have a behavior where we cannot take the log of a negative number or 0, so x has to be defined as greater than 0 here. You might think that that means that it's definitely discontinuous, since only values above 0 are going to work for this function. But let me create a quick sketch of the log graph. So log graph looks something like this. It's the inverse of an exponential. And we can trace it without lifting our highlighter, right? We can actually trace the length of this function. So just because it's only defined over a certain interval, it is a continuous function because it is continuous over that interval. A function does not have to have a domain of all real numbers in order to be continuous. So now let's just kind of tie it all together. I've given you a graph here of some sort of a piecewise function, and the question is asking us to identify the intervals of continuity and to identify each type of discontinuity. So you guys can go ahead and pause the video and give this one a try, and then unpause when you're ready to see the answer. So this function has intervals of continuity. It starts off at negative 4 in my x direction, and I'm heading towards negative 2. At negative 2, we have a hole. We pick up from negative 2 to 1. We pick up from 1 to x equals 3. And then we jump up to 3 to infinity. So this is my interval of continuity. This is what you guys need to be able to write. Our discontinuities occur at x equals negative 2, which gives us a hole, x equals 1, which gives us an infinite discontinuity, and x equals 3, which gives us a jump. Note that you have one discontinuity for each of those union symbols within your interval notation. And we do want to specifically name the type of discontinuity, and we want to make sure that we identify the x value where it occurs. So this type of a written out solution is what would give you full credit on an assessment for standard 3 continuity. Thank you guys.